So I hope Kirchhoff's laws make sense to you, right? We can continue with electrical measuring devices. Let me start with galvanometer. So practically galvanometer is something that measures current. Okay? That's what it is practically. So let's say 0, and let me call this IFS, which is full scale current. Okay, so it can measure current, but this full scale current is not that large. It might be 1 milliamperes, let's say. How does it measure it? So it basically has an N part of a magnet. Of course, we haven't seen these parts yet. We don't know what is the interaction here. But basically it has a magnet and some coil, okay? And when there is a current going in, the coil would bend. But there is another coil that is against this bending. So a certain amount of current would only go a certain amount of bending. Okay? There will be an equilibrium there. So maximum amount of current, maximum amount of deflection. Okay? So it's about deflection. And in the maximum amount of deflection, we read the full scale current. So this is the galvanometer, but galvanometer is the basis for both ammeter and voltmeters and any really electrical meters. At the end of the day, they end up with galvanometer. Okay? So how you can build ammeter from galvanometer? What does ammeter measure? Which is current. It measures current, right? You might ask me, isn't it just galvanometer? Doesn't it measure current? Why do we need ammeter? Well, galvanometer measures up to 1 milliamperes, let's say. But ammeter can be designed to measure anything, really. So let's say this is my ammeter. And what happens here is that you have a galvanometer here, which has a deflection. So let me say it's right now pointing at full scale deflection. And its coil has some resistance, right? RC. This is resistance of galvanometer coil. Okay? What you do is you put a shunt resistance here. All right? RSH. Why do you put it? Because you want to use this full scale current but you want to measure a different current, different maximum current. Let's say you want to measure I max, right? So from this consideration, what do we have here? We have here IFS, and over here we have I max. Let me just I max minus IFS. Do you agree with that? The current over here is I max minus IFS. Any problem with that? No. So do you agree that the potential between these 2 points, is either IFS times RC, so IFS times RC, or the same potential difference can be written as I max minus IFS times RSH. Did you follow this? Yes? So I max is practically IFS times RC over RSH plus IFS. Okay? So you can change RSH, and by changing RSH you can achieve any maximum current you want. That's what's happening with your multimeter when you are changing it to measuring mega ohms, kilo ohms and stuff like that. I'm talking about ohms, sorry, milliamperes, amperes, whatever. Do you follow? So it changes the shunt resistance. Any questions? So galvanometer stays there, but its full scale deflection corresponds to different currents because you change the shunt resistance. That's how it works. If you have no questions, I will continue. All right. Let me also talk about voltmeter really quickly. Sure. Let me do it this way. Thank you. Now for voltmeter, let's say this is my voltmeter. I will use galvanometer again. So same story. I have a galvanometer here, and let's say it's right now showing the full scale deflection, and it has a resistance RC. But now I will add a series resistance to this, RS. RS is series resistance. Okay, by adding this series resistance, I will be able to measure different voltages. Okay, so basically, let me do it this way. Let's say I have a wire here. Are you done? Can I zoom in? Yes? So let's say there are 2 points here, A and B, and I connect my voltmeter there, and there is some current, bless you, IFS. So full scale current flows through here, over here, and the potential difference VAB, let me call it V max, will be IFS times RC plus RS, right? So as you can see, this time I can change RS as I wish to measure higher and higher voltages. I can change it such a way that maximum deflection in the galvanometer current corresponds to maximum voltage that I'm going to measure. All right? Good. So usually what we do is we make RS large, right? And we always measure voltage in parallel, right? We connect it in parallel. And with the ammeter, we usually make our shunt as small as possible, as small as needed, let's say. But usually it's small, so you should be connecting ammeter in series. Because if you connect it in parallel, then it will be under a huge voltage and it can burn. So far, so good. There is also a part about ohm meter, but I think you should read it on your own. Okay? All right. Now back to fun stuff. Back to fun and not so easy stuff.
Does galvanometer sustains the voltage difference for the circuits?
Sustains?
I mean,
Supplies. Do you?
yes.
Yes.
Like creates the.
No.
No. Then where we put the button.
So, okay, very good question. So for voltmeter, you don't need a battery, right? It just measures voltage.
Yes.
So if there is a voltage, it will measure it. For ammeter, if there is a current, it will measure it. But for ohm meter, you need to have a battery inside your measurement device. Did you follow? That's when you need the battery. RC circuits. So this is the second big topic for you. Okay, there were this electric field, potential, and stuff like that. That is one chunk. Now it's RC circuits. Yet another chunk where you might get lost because of you might be scared of stuff. So don't be. Okay, it's not that hard. All right. So I want you to always have at the back of your head this system. We will talk about electricity, but I want you to remember this first. Do you remember this stuff? Mm-hmm. Harmonic oscillator, right? So harmonic oscillator would say that F equals to ma, right? This is Hooke's law. Hooke's law. This was someone's law, I forgot. Yes. Newton's law, right? So if you put them together, you have ma equals to minus kx, or ma equals to, plus kx equals to 0, or md squared x over dt squared plus kx equals to 0, right? This is simple harmonic oscillator. Just making it a little bit harder is to add friction. You can add friction, right? Let's say it's moving with velocity b. You can add friction, which is minus b times v. Have you seen anything like this? This is damped oscillator, right? If you have damping, then your m d squared x over dt squared still has this Hooke's law, but it also has this minus b times v. So eventually, damped harmonic oscillator has m times d squared x over dt squared plus b times dx over dt plus k times x. Okay? Does anyone know why I reminded you this? Anyone has a guess?
I think we are going to deal with differential equations.
Yes?
In like RC circuits.
Yes. Very good. Eventually, we will have a one-to-one correspondence there will be literally no difference between a mechanical system, damped oscillator, and an RLC circuit. So eventually we will reach there. This will be the L part, this will be the R part, this will be the C part. Okay? It will have one-to-one correspondence. Okay? So always keep that in your mind. Now let's start with RC circuits. Oh, we already started. Right? So let me draw you an RC circuit. Let me modify it a little bit. I also have a switch, S. Okay? So what happens is that S was in this position, in the position A, for a very long time. What happens after very long time?
Capacitor is charged.
Capacitor is charged. Does everyone agree with this? Yes? So capacitor is charged. Is there any current flowing? No, right? Capacitor is charged. So what happens is that capacitor has, so this is plus, this is minus, this is plus, this is minus, and it has some Q0 over here, which provides like exactly the same amount of voltage difference, right? So that, let me just say, let's say this is point A and this is point A as well. I mean, in terms of the potential, right? These 2 points have the same potential right now. Also, what happens is that since current is 0, the potential difference over here will be 0, and the potential difference across here will be the same as the potential difference across here. Okay? So far, so good? Do you have any questions at this point? No. Yes?
Hocam, we are saying that current is zero because the capacitor is charged.
Yes, exactly. Exactly. Very good. Current is 0 because the capacitor is charged. Didn't need to be 0. There has been a stage where it wasn't 0. Okay. Actually, let's investigate that stage. So let's investigate the situation where, let me just erase this part over here. So the switch was like this, and there was Q equals to 0 over here. Okay, where are you? What was your name? Onat. And yours? Ömer. Ömer and Onat. Okay. Onat. What I will do is, at t equals to 0, I will switch S to A. Okay? Then what will happen? Will there be a current?
Yes.
There will be a current, because that way the capacitor gets charged. So at a certain time, there will be a current flowing, I, and there will be some charge plus Q here and minus Q here. Good. So I can apply Kirchhoff's law. Right now the switch is closed like this. And I start from home over here. I have plus E. I'm going this way. I have plus E. Do you have any objection here? No. There's a river flowing away from me, right? Minus I times R. And then? What is the final one? Q over C. And is it plus or minus? I'm going from plus side to the minus side, so minus Q over C equals to 0. All right? But we are not done. We also know that the change in this current over here, plus Q, is related to this, the change in this charge is related to the current. How is it related?
It is derivative.
Yes. Well, it depends which one is your main character. So let's say Q is the main character. Then the change in Q corresponds to
Derivative.
current. So I is going to be dq over dt. Do you have any objection to this? Any comments? So this is nice because I have two variables, right? And I have two equations. I can, yes,
Why I is not Q over T directly and GT over?
very good question. So it's instantaneous current. Current at that moment. Current at that moment. Yes, at any moment t. Yes, instantaneous current. Yes.
We first close the switch and open it and close it again, right?
Yes, I think I didn't plan my thought process there well. So let's start from open, no charge, and then I close and forget about before.
Okay.
Okay? Instantaneous current. Good. So can you tell me what happens if I put this in this equation? I have the same equation. E minus, instead of I, I'm going to put dq over dt minus q over c equals to 0. Right? So let me rewrite this equation. R times dq over dt plus 1 over c times q minus e equals to 0. I didn't really need to do this, but I'm going to remind you this. Copy and let me paste it down here. So, do you see the correspondence here? This one corresponds to this because like q goes to x, this one goes to k, this one is this one is that one. And we just don't have L in the system, okay? And what is E? E is just a constant, okay? It is like a constant force pulling on the string. So, are you happy so far? What would happen if you had a constant force pulling the spring, sorry, and there is no inertia? What does it mean when you have no inertia? Please pay attention. I'm going to tell you something very important. Can you imagine a mechanical system which has no inertia? It's not affected by the forces. it is affected by the forces. Can you imagine?
If there is no mass, there is no inertia.
Actually, it's
I mean special
It's-
relativity. Bu da olur mu? Yok, bunda da mass.
Maybe no torque.
Can we say if it has no inertia, it cannot have any momentum?
okay. Let me tell you this way. Actually, no inertia is more familiar to us, to our brains, than yes inertia. Let me tell you how. This is an object, right? I push it, it moves. I stop pushing, it stops, right? But Newton's law tells you that you push something, it accelerates, you stop pushing, and it just keeps moving, right? So in real life, usually friction wins, right? So friction is much higher than inertia, much higher than inertial forces. That's why I think when we push, they move. When we stop pushing, they stop moving, right? So when I say no inertial system, think about something moving in highly viscous fluid, like honey. Okay? Now imagine your mass spring system in honey, and it's being pulled by a force. What will happen? So I started like this. I have M, K. M doesn't matter really because we are not dealing with inertia, but it's in a honey. So how should I represent honey? It's in a okay. Üstüne honey yazayım. Very good. Okay, everywhere it's honey. Okay, now I'm pulling with some F0. What will happen to this system? Slows down and stops, but it stops at a certain distance, right? So if this was the equilibrium point, it will just move over here, let's say, to some place x0, and will stop there. Are you following? Yes or no? This is exactly what happens with RC circuit. So the potential is like the force pulling it, and we will eventually reach at a certain charge, which, remember, was corresponding to position, right? We will reach a certain charge and we will stop there. Are you with me? Yes? Good. So let's now solve. Now we have some imagination about the system, a physical intuition, let's say. Let's now solve the equation without thinking about any physical intuition, just doing mathematics, okay? So here is how I usually treat this problem. I usually want to have, okay, let me just write it down. Do you agree that minus r dq over dt is equal to q over c minus e? Do you agree? Yes? Then if I multiply both sides by c, do I get minus rc dq over dt equals q minus ce? Yes? Do you agree that if I write dq over q minus ce equals minus dt over rc? Do you agree to this? Yes? All these steps were pure experience, and you should do it multiple times and you will get the same experience. So what I did is I knew that first of all, I want to collect q's on one side and t's on the other side. I have achieved that. Second of all, I knew that I'm going to have an integral which will give me an ln, and I didn't want to bother with the coefficients, so I made sure that q has no coefficient in front. That's why I multiplied with c. Okay? But otherwise, now it's time to integrate, and I will start from 0, go to t, and I will make this one t prime so that I obey the rules. Okay? And I will integrate from 0 to q, and I will make this q prime. Okay? So what is the left side integration?
ln q prime minus ca from 0 to q.
Everybody agrees with this? Ln q prime minus ce to be evaluated at q and 0. And the right hand side is t prime over minus t prime over rc to be evaluated at 0 and t. Did you follow this part? So I have I have ln q minus ce minus ln minus ce equals minus t over rc. Are you happy with this? Am I going too slow? Huh? Do we have time? We have time. So ln a minus ln b is
ln a over b.
a over b, yes. So q minus ce over minus ce is equal to minus t over rc. Now let me take the exponential of both sides. Q minus ce over minus ce is equal to e to the minus t over rc. Q is equal to ce minus ce times e to the minus t over rc. Q is equal to ce times 1 minus e to the minus t over rc. And this is capacitor charging. All right. This is Q of t. I hope you followed this. So if we plot this, let's plot this. Didn't understand it? Okay. Third one is the charm. Yes. So I have my Q. What happens to Q when t is 0?
T is 0, q is 0.
T is 0, Q is 0. Everybody agrees with this? Yes? Because e to the 0 is 1, 1 minus 1 is 0. What happens when t is infinite?
Q is equal to ce.
Q is equal to ce. That's right. So it approaches c times e asymptotically. This is c times e, and it approaches c times e asymptotically, right? This is 0 here, 0 here. Of course, there are some stuff here that you already know, probably. There is this definition of tau, which is r times c. We call it time constant. So what happens when you reach tau? Let's say this is tau. What do you have in Q over C? Is what is the value of Q when you reach tau?
Ce 1 minus 1 over e.
CE 1 minus 1 over E. Everybody agrees with this? Everyone? Yes? How much is that?
Allah bilir.
So what is 1 minus 1 over e? Can you calculate, please? Hmm? No. It should start with 6, 3. Let me do it myself. 1 minus 1 over 2.71. It's 0.63, okay? And something. So you reach 63% of your charge at the time tau. So it tells you how fast you are going to charge, right? Let's think about it. When resistance is low, right? Your time constant is low, which means that you are charging fast because your resistance, there is no resistance against charging, right? So you charge faster. When capacitance is low, you charge faster because you need to charge lower amount of charge on the capacitor because its capacitance is low. Do you see? Do you have any questions? Is it scary? No? So remember, this Q was corresponding to X in our analogy, mechanical analog. And just like in the mechanical analog, we were expecting this system to go like T, x0. We were expecting X to approach some x0 like this. It's in the honey. You are pulling it, and at first it comes a bit faster because the spring is not what do you call it, stretched yet, right? So it comes out faster, but then when it's equilibrated by the spring force, then it stops. And there is no oscillation because it's in a honey. Okay? Yes? Yes. Sure. Sure. The question is, what are you talking about, hocam? Honey, mechanics, RLC, right? What is the... Yes. So, I'm trying to, in case you can't imagine charges moving up and down, you can always imagine springs, right? It's mechanical, you have seen springs and stuff like that. So I'm telling you that RC circuit is an exact analog of a mass spring system inside a honey. That's what I'm saying. Whatever happens to the mechanical system happens to RC circuit. Whatever happens to RC circuit happens to mechanical system. You just need to remember which one was analog of which one. So X is analog of Q. Okay? V is analog of current. Okay? K is proportional to 1 over C. B is proportional to R. And B is the friction coefficient. Thank you. So, I hope you have followed so far. Should we switch it back to position B? So this was for charging. This is charging. Now let's take our capacitor from here, our system from here, and let's switch to the other side and talk about capacitor discharging. So this time at at t equals 0, I define a new t, new clock. At t equals 0, I switch this from A to B. Now what do I have? I have just RC circuit, and at time equals 0, it's fully charged. It has C plus CE here, minus CE here. Right? I will understand if you answer this correctly. What is the corresponding analog of this, what we just did in the honey system?
Removing the honey?
No?
Releasing the string.
No? Ah, releasing the string, yes. I mean like releasing the force, right? So if you take away the force, remember this E, the battery, was the force, right? And we stretched it to x0. Now, I will release the force. So what will happen? We expect it to suddenly come back and smoothly go to equilibrium. Do you understand? No? There is honey, there is spring, there is mass. I pulled it, and I applied constant force, and it came down here, right? How did it came? It was fast at first, but then slowed down. Now I release it from here. It will go fast, quickly like this, but then slow down at equilibrium. And it will not overshoot. It will not do this. It will not do that because there's no inertia. There's so much honey that it always follows the force. Do you see? Yes? So without even solving this problem, what is the Q that you are imagining? What do you expect for the change in Q? It starts at C times E. So how would you draw the plot? No, that's charging. That's charging. Now it's discharging. It starts from here. Like this. Suddenly goes down and then just drops to 0. Yes? But now let's solve it. Let's actually solve it. Do we have time? We have 3 minutes. So we actually have the same equation, only we are missing E. Do you remember the equation? This is the equation, and we don't have E in it. Copy. Just paste it here. And remove E. Okay? So what do you have? Much simpler system. You have dq over q equals to minus dt over rc integrated from 0 to t. Let me make it t prime. Integrated from
Q to 0.
ce to some q at a certain time, right? So I have ln q over ce equals to minus t over rc. I have my q of t equals to c times e to the minus t over rc. And this is capacitor discharging. Let me just pull it to the left. And this is the formula for capacitor discharging. Okay? How does it look like? Basically has, just like I mentioned earlier, but let's plot it again. So you have some CE starting at CE and going like this. Okay? Do you have any questions? No? So at t, at time t equals to tau, it decreases down to what? CE times 1 over E, right? 1 minus 1 over E was 0.63, so this must be 0.37, yes. So it approaches 0.37. Okay? Do you have any questions, comments? No? Let's have a break.